All right, so let me begin by thanking the organizers for giving me this wonderful opportunity to present our recent work. So this talk is going to be based on a paper we wrote with Vijay Balsubramanian, Matt DeCross, and Arjun Kar, and Matt and Arjun are excellent graduate students at UPenn. So an important question in the idea CFD correspondence is understanding which class of quantum systems admit a nice gravitational description. And for this purpose, identifying sort of universal probes of gravitational dynamics is of significant interest. So several criteria, such as spectral properties, chaotic dynamics, entanglement structure, have already shed some light on this question. And recently, quantum complexity has been proposed as a possible probe of such gravitational dynamics by Susskind and collaborators. So the observation was that in a two-sided the eternal black hole geometry, the volume behind the horizon of the black hole sort of keeps increasing linearly with time indefinitely into the future. And this phenomenon was conjectured to be dual to the growth of complexity in the dual CFD state. And since then, there have been several works on complexity, in particular in gravity, trying to understand this better. So what is complexity? At least in terms of qubit systems, we can think of complexity in the following way. So we start with some initial fiducial state, which is you can take to be completely unentangled. And then we build some circuit with some simple gates that you're allowed, and sort of we try to build some given state psi using such a circuit. And then the minimal number of gates you need to do this is what you might call the complexity of the state psi. So you can really think of complexity as some kind of fine-grained probe of the entanglement structure of this final state psi. But in order to make contact with gravity, we need to generalize this kind of definition to more general systems, in particular quantum field theories, what do we mean by simple gates, and so on and so forth. And much progress has already been made, but in particular in these papers, but a lot of work still needs to be done. OK, so one universal feature of complexity, though, is the fact that the complexity in gravitational systems should grow linearly with time for a long time of the order exponential in the number of degrees of freedom. And then it should saturate for a doubly exponential time. So this was a conjecture in this nice paper of Brown and Susskind. And so our aim here will be to try and move towards a proof of this conjecture, or to try and understand this particular behavior of the complexity, in particular for large and chaotic systems. The sort of working example that we will consider in this talk is the SYK model, but most of our arguments should generalize to more general large and chaotic systems. And this is somehow in the spirit of the question that Brian was mentioning about what is the relation between chaos, complexity, and gravitational dynamics. OK, so to be concrete, we will take Nielsen's geodesic approach to complexity, which is a geometric approach. In this approach, we think of complexity as the length of some minimal geodesic in the space of unitaries. So just to unpackage that a little bit, let U be the space of unitary operators acting on the Hilbert space, and a little u, its corresponding Lie algebra. Then in this Lie algebra, we are going to identify some generators, let's call them T with a subscript alpha, which we will declare to be simple, and and the rest of them, where I put an alpha dot on the subscript, as being hard. Okay? So for example, in the SYK model, you can think of the simple generators as being built out of these elementary the Majorana operators up to k fermions. So basically, all the k local operators of the theory you might take to be simple, and all the operators which are have more fermions in them may be hard or maybe declared non-local. And just to note, we will always pick this k large enough so that the Hamiltonian of the system is always built out of simple generators. So in the usual SYK model, for example, we take k to be greater than 4. Okay, so now we need to pick a metric on this space of unitaries, which in this case is simply SU2 to the n over 2. And this metric is supposed to encode your information about which directions are easy and which directions are hard. And for the SYK model, for example, a good starting point is so what you do is you start with the Killing form on the Lie algebra. In the SYK model, this is simply the identity matrix. But in order to encode this notion of complexity, we have to modify this bilinear form a little bit. So but we add in cost factors into this bilinear form by hand. These cost factors are chosen so that if in the directions which are local or k-local, this cost factor is simply 1. But when in the non-local directions or the hard directions, the cost factor is modified to be 1 plus mu, where this mu is some positive and eventually large number. Okay? And then on the full space U, the full group, we take the metric to be the right invariant metric, which comes from this particular bilinear form. Okay, and now I've told you the metric, and so the complexity of some operator, let's say U, we are going to be in this talk mostly interested in operators of this form, e to the minus IHT, just the time evolution operator. So the complexity of such an operator will be the geodesic distance in the metric that I described from the identity to that operator. Okay, and so it's been argued in several of these papers that you can think of this complexity, this geodesic version of the complexity, as some kind of approximation to the usual notion of circuit complexity. In particular, if the cost factor that I talked about is exponentially large, then this geodesic complexity is at least polynomially equivalent to the circuit complexity. All right, so now, as I said, we are interested in computing this geodesic complexity in the case of the SYK model, and the endpoint will be the time evolution operator of the SYK model. So you can parameterize geodesics on this group manifold in terms of these sort of path-ordered exponentials as usual. And this object here that's appearing here is what I'm going to call the velocity. I've written it here in terms of its components, but you can also think of this whole object as an operator. And in terms of this operator, the geodesic equations take this particular form. Here, the subscript L stands for projection onto the local directions, the k-local directions, and the subscript NL stands for the rest of them, so the non-local directions. Okay, and the boundary condition is that you end at this time evolution operator. Okay, so what do we have to do then? So in this framework, if we want to somehow prove this or understand this kind of behavior, first of all, we need to find a geodesic whose length will grow linearly with time. Then we need to show that this geodesic is actually a local minimum. In other words, that it's not a saddle point, and that it's a local minimum at least till exponential time. And then we also need to argue that there are no global issues, that this geodesic is actually a global minimum, but maybe after exponential time, there are other global minima or other geodesics which take over, and that leads to the saturation of complexity. Okay, so the first task is pretty easy. So it's a simple exercise to show that if we pick the velocity to be simply h times t, and as long as the Hamiltonian is only built out of simple generators, then this particular geodesic that I wrote down here is actually a geodesic. And then the length of this geodesic is also not hard to calculate, and you find its length grows linearly with the time, of course, because there's a t sitting right there. Okay, and the coefficient is basically the root mean squared energy of the Hamiltonian defined here. So one thing to note is that this geodesic essentially entirely lies along the k-local or the easy directions in the group, and so that's why the length of this geodesic basically does not depend on the cost factor mu that we introduced. Okay, so this part is really pretty simple. But now the challenge is to show that this geodesic that you found, or we found, is actually a local minimum and more generally a global minimum. Okay, so that's going to be where the interesting physics lies. So here, for now, we'll mostly focus on the local minimality of this geodesic. And the way you check that this geodesic is a local minimum is you show that there are no conjugate points along it. OK, so what is a conjugate point? So say you have this linear geodesic out here. We'll say that there's a conjugate point at some time t star if you can find an infinitesimally nearby curve along which you travel and you come back to this original linear geodesic at this time t star. And by infinitesimally nearby, I mean that this curve sort of satisfies the linearized geodesic equation around this original linear geodesic. Okay, and so if you can show that there are these conjugate points, then that means that the original geodesic stops being minimizing after the first conjugate point. In particular, it becomes a saddle point after that. Okay, so these are the linearized geodesic equations around the linear geodesic. In particular, so these are what are called the Jacobi equations. I've written them here in terms of the velocity, which is most natural in the present case, and the boundary condition that you come back to the original geodesic at some time t is this condition here. So before I call the conjugate point t star, but for notational simplicity, I've just dropped the star and just called it t over here. OK, so then we need to show that these set of equations have no solutions, at least till exponential time. OK, so the strategy that we'll follow is that instead of trying to solve these equations here, we'll essentially change the boundary condition a little bit, and we'll solve these differential equations with an initial condition. So we pick some initial velocity delta v naught. And then once you've done that, you can go ahead and compute the deviation of the endpoint of this geodesic. Because everything is linearized, the geodesic deviation at the endpoint will be a linear function of this initial condition. Okay, so then you can think of this operator, which I'm calling y. It's more like a super operator because it maps operators to operators. But you can think of it as a linear operator, which will take your initial condition or the initial velocity deviation and map it to the final the deviation of the endpoint of this geodesic. Okay, and then we say that we have a conjugate point if this operator develops a zero mode at some time t. Okay, so then it's pretty natural, pretty clear what we must do. We must study the spectrum of this operator y. By the way, this operator depends on this cost factor mu and the time t as their internal parameters which appear inside this operator. Okay, so just as a warm-up example, we can look at how this works at mu equals 0, where we set the cost factor to 0. Here, there's essentially no distinction being made between the easy and the hard directions. So here, the problem is really simple. You can pretty easily work out what this operator is. And in particular, you can also get its spectrum pretty easily. So these are the eigenvalues of this operator. And here, m and n, these things here are just the energy eigenstates of the original Hamiltonian. So here I've just plotted one of these eigenvalues, or the absolute value of one of these eigenvalues for a particular one. And you see that the absolute value drops to 0 at lots of points. And so these are all the conjugate points along the linear geodesic. So in particular, these happen at those values of time. And for example, the first conjugate point that you encounter happens at this value. So for example, you can look in the SYK model, and this happens at a time of order 1 over n. Okay, but that's not very surprising. This was the mu equals 0 case. We weren't really making any distinction here between the simple and the hard directions. So it's not surprising that you develop conjugate points early on. So really what we want to do is we want to track these conjugate points as mu becomes large and show that they move off to large times. So in general, tracking these conjugate points at large mu is not that simple. In particular, the sort of complication happens because these Jacobi equations have projections sitting on the right-hand side. So in particular, I'm supposed to compute this commutator and then project it on the local directions, and similarly here, project along the non-local directions. However, the problem simplifies greatly in large N chaotic systems. So the main reason for this simplification is the following observation. So if I take an outer product of two energy eigenstates, M and N, with basically off-diagonal energy eigenstates, by which I mean the energy of EM or M is not equal to the energy of N, then the local projection of such outer products are exponentially suppressed. Okay? So said another way, these kind of off-diagonal outer products of energy eigenstates are essentially non-local in large N chaotic systems. Okay, so if you want some intuition, is that if you take two microstates of the system, then mapping one to the other is an essentially non-local or a complex operation. You can test this in the SYK model by simply computing this object, and here I've plotted this object as a matrix, and you see very nicely that all of these off-diagonal elements are exponentially suppressed. And you can also check that by making a histogram of them. Okay, so this hypothesis, this criterion is what we call the Eigenstate Complexity hypothesis in our paper, essentially because it's saying that the off-diagonal products like these are complex, or there's some complexity in the eigenstates of the Hamiltonian. But in the SYK model, you can also argue this from the usual eigenstate thermalization hypothesis. Okay, so now with this observation in hand, you can go ahead and try to compute the spectrum of this operator y at finite mu. Okay, and I'm going to spare you the details, but at least if mu times t, where t is the time, is much smaller than e to the s, then you can actually compute explicitly what the spectrum of this operator is, and these in particular, these are the eigenvalues. Note that this cost factor mu now enters in this spectrum in an essential way. Okay, so now once again you can calculate where this eigenvalue drops to 0, and you find that the conjugate points happen at these particular values of time. Z is integers, but in particular the cost factor mu enters these conjugate points, and here's what it looks like. These were the original conjugate points at mu equals 0. When you crank up mu to be large, all of these conjugate points sort of move off to large times. And in particular, if you take this cost factor to be exponential, then these conjugate points move off to exponential times, okay, in large N chaotic systems. So then what this shows is that in large N chaotic systems, the linear geodesic is at least a local minimum of this complexity function for exponential values of the time, till exponential time. Okay, but we don't. So this sort of shows local minimality, but we do not have yet a proof of global minimality of this linear geodesic. However, we can make some comments or some partial progress in this direction. So as before, it's a good idea to first start with the mu equals 0 case, where we set the cost factor to 0. Okay? So when you set the cost factor to 0, it's a pretty simple exercise to work out all the geodesics and see what they're doing as a function of time. And in fact, here I've plotted the full complexity as a function of time. Each of these curves that you're seeing here is one particular realization of the SYK model. Okay, so I plotted them for several different realizations. And you see that what the complexity does is it grows linearly in time for some time, and then it saturates. Okay, so what's happening here is that this part of the behavior is basically dominated by the linear geodesic, which is why the complexity grows linearly. And then at some value of the time, other more non-trivial global geodesics take over, and that leads to the saturation of complexity. However, this is the mu, remember this is the mu equals 0 case, so for that reason, the saturation happens way too early. It's given by this particular time scale. But when you turn on mu and make it large, basically all but the linear geodesics will sort of get affected by this cost factor and will move to larger and larger values of complexity. And so for that reason, we expect that the linear geodesic will sort of dominate for larger and larger times. And this is the kind of physics we also saw in our analysis of conjugate points. Now, it's kind of easy to find, so a cautionary remark is that it's easy to find Hamiltonians, in particular integrable Hamiltonians, where you can explicitly demonstrate that there are non-trivial geodesics which sort of start competing with the linear geodesic at early times, at order 1 times. Okay? So if that happens, then what you find is that the complexity sort of just grows and it comes back down, grows and comes. So it has some kind of oscillatory behavior. Okay? But this kind of phenomenon happens because there are non-trivial geodesics which lie entirely within the simple direction. So somehow the simple or the local directions in your group manifold. You can argue that for chaotic Hamiltonians, such geodesics do not exist. Okay, there are no geodesics. There are no non-trivial geodesics other than the linear one, which lie entirely within the simple directions, and so at late times start competing, or at early times, sorry, start competing with the linear geodesic. But the details of this proof are a little bit involved, and there are sufficiently many subtleties that I won't go into the details over here. All right, so to summarize, we studied the time evolution of complexity in large and chaotic systems using the Nielsen formalism. We argued that there is always a geodesic whose length grows linearly in time. We showed that in large and chaotic systems, this geodesic is a local minimum, at least a local minimum, till exponential time. And although I gave you some arguments for global minimality, we don't have a complete proof, and so it would be nice, or it would be interesting to come up with a proof that this linear geodesic is a global minimum till exponential time, and in particular understand how complexity saturation works. And it would be very nice if this kind of proof involves some property of chaotic Hamiltonians, such as spectral statistics, eigenstate thermalization, or something like that. In our proof of the local minimality, we saw some version of this appearing in the form of eigenstate complexity, but it would be interesting to understand the full story in the case of global minimality. And so this kind of reasoning may eventually lead to a deeper understanding of the relations between complexity, chaos, the entanglement structure in the CFT states, and the emergence of gravitational dynamics in the ADS-CFT correspondence. Thank you.
Questions? Yes.
Onkar, I got confused. You probably mentioned this, but this parameter mu, you had the freedom to choose it. You derived the formula, and then when you choose it to be itself exponential, then you got doubly exponential in complexity. So what is the reason for choosing it to be exponential rather than just wanting to match the result?
Right. So it's been argued by Nielsen and collaborators that when you tune the parameter mu to be exponential, then the complexity becomes polynomially equivalent to the circuit complexity. So remember that this is a different type of complexity. So we are computing the geodesic complexity in this formalism, you can always sort of ask how that is related with what you might mean by more discrete or a more sort of circuit version of the complexity. And the argument is that when you choose this parameter to be exponential in the system, the size of, or e to the s basically, then this geodesic complexity closely approximates the circuit complexity. So for that reason, you would want to pick this parameter to be exponentially large. But there is still some discussion and debate in the literature about what exactly you should pick this parameter. Maybe you should pick it more locally depending on which which generator you're looking at, and so on and so forth. So this is, you can regard this as some further evidence that when you choose this parameter to be exponentially large, you know, the complexity demonstrates the right kind of behavior. It grows linearly with time till exponential time.
Can you elaborate why did you say that for chaotic Hamiltonians you expect the linear geodesic to dominate? I mean, what are the assumptions that go behind that statement?
So you mean the local minimality or global minimality?
Local minimality for now.
Local minimality. So that, so as I showed in this, let's see if I can find the right. So basically, the assumption is this one, right? So to show local minimality, we want to show that there are no conjugate points till exponential time. To show that, the basic assumption that went into the analysis is that these kind of outer products of energy eigenstates or off-diagonal energy eigenstates are essentially non-local, or in other words, their projection on the local directions is exponentially suppressed. And that's where we tested it in. So this phenomenon happens in large N chaotic systems.
But that doesn't explain why there are no other non-trivial geodesics. You're just looking at the fluctuations around a local geodesic. So but this doesn't say that this is the operative feature that the complexity, whatever it is, grows linearly in time.
That's right, that's right. So, so as I said, this is what guarantees local minimality. So absence of conjugate points means local minimality. If you want global minimality, which is to say that there are no sort of non-trivial global geodesics which come and start dominating, that's a harder problem. And there are some, as I said in my last couple of slides, there are some indications that integrable Hamiltonians just don't satisfy this. So you can find explicit examples of integrable Hamiltonians where this doesn't happen, like there are other geodesics which compete with you. But we don't have a complete proof that there are other, for all chaotic Hamiltonians, this never happens.
Any other questions?
I just wanted to know if you knew whether these hardness results that you're looking at are robust, if you're interested not in truly minimizing geodesics, but rather just relatively short geodesics for the purposes of circuit design.
I'm not completely sure what you mean by that. Could you elaborate on your question?
Yeah, so you know that finding the absolutely minimal geodesic in your conjugate point analysis, if mu is tuned to be exponential, will be doubly exponential. But say I'm not interested in finding the actual minimal geodesic, I'm not finding the most efficient possible circuit, but say I'm interested in finding a circuit that has 10% more gates, or some error tolerance there. Do you have a sense in which this difficulty that you're alluding to of the doubly exponential time scaling is robust to this sort of tolerance in the minimal complexity?
Yeah, that's a good question. I don't think these methods can be applied in this situation where you have some, I mean, maybe by suitably modifying, so, okay, most of the analysis was studying conjugate points and Jacobi equations and so on. So maybe you can modify the Jacobi equations in some suitable way by introducing these small tolerances into that equation. We haven't really thought about that very much, but it's a possibility. I don't have a concrete answer to your question.
There's a question there.
Okay, so it's another one about the penalty factors. You are dividing the easy and hard directions, right? And you have just one penalty factor associated to all the hard directions, but usually in the Nielsen construction, you have, I don't know, bilocal, trilocal gates, and they get penalty factors which go with some power of a constant. And then, of course, like when you have very hard direction, they would have maybe exponential cost, but can you, say, repeat this exercise for a system in which you have graded penalty factors?
Yeah.
Would you get the same?
Yeah, no, that's a great question. So as a first step, we sort of just focused on the case where you put a hard cutoff. You say that all of the k local operators are simple, everything else is not simple. So this is kind of a hard cutoff thing. You can also try to put a soft cutoff where you like do what you say, like have a graded cost factor and so on. We haven't explicitly tried to do that, but at least as far as this eigenstate complexity goes, or at least the sort of local analysis of trying to study conjugate points and so on, I expect that this analysis should go through in your sort of graded cost factor point of view, but that's something to be done. That we haven't done it.
Thanks.
Yeah.
Okay, let's thank Onkar.